Okay, section 7.2, sample proportions. In section 7.1, we looked kind of generically at the idea of a sampling distribution, where we're taking every possible sample of size n, and we're calculating the the sample statistic related to the population parameter that we're interested in, and we're looking at all of the statistics related to all the samples. So now we're going to specifically look at the sampling distribution for proportions. So recall the distribution of the population. So think about the big jar of pennies. The distribution of the population would be the dates for all of those pennies laid out in a big dot plot. If I take samples of those pennies, let's say I'm taking samples of size 10, I'm looking at the dates, and in this case, since I'm talking about proportions, maybe I'm interested in the proportion of pennies that have a date of 2000 or higher versus those that have a date of less than 2000. So again, here, looking at each sample, I would look at all the dates of all the pennies, and then I would calculate the proportion for each sample, and that's the sampling distribution of the statistic. That's what that would look like. Recall, a proportion refers to the fraction of the total that possesses a certain attribute. Here's a different example. We might ask what proportion of dogs in a sample weigh less than 35 pounds. Suppose on average 3 dogs out of 5 weigh less than 35 pounds. The population proportion then would be 3/5 or 0.6. This is not to be confused with the mean, which would be the average weight of all the dogs. Here's a different example. Suppose, according to the CDC, in 2015, 15 out of every 100 U.S. adults were smokers. How much would we expect the proportion of smokers in samples of size 100 to vary from sample to sample? We're going to simulate this, and one way to do that would be to set up a random number generator where we would assign numbers 1 to 15 to represent smokers and 16 to 100 to represent non-smokers. Draw samples of size 100 over and over again, which would be rather tedious to do. We're going to look at a way to do that using an applet in a second. But if we did this, we might get a distribution that looks like this. Okay, so notice, what are we looking at here? Each of these lines is made up of lots of dots. Each dot represents one sample. It represents the proportion of smokers in that sample. Notice that the mean of this distribution is about the true value of the proportion of smokers, 0.15, 15 out of 100. So that's right about here. So the mean of the distribution is equal to the population parameter, P. What about the standard deviation? That measures the spread. Okay, so how do we calculate that? That's what we're interested in. Recall that for a binomial distribution, let me just skip over here so we can recall binomial distribution, where we have, in the binomial distribution, we're interested in success or failure. We have independent trials, a fixed number of trials, and the probability of success the same in every trial. So in our smoking example, you're either a smoker or you're not. Trials are independent. Here we're drawing without replacement, where we're drawing from such a large population that the trials can be considered to be independent. We're drawing a fixed number of people in each sample, and the probability of success is the same for every trial, 0.15. All right, so the formula for standard deviation from Chapter 6 we learned is equal to this. Notice that it's dependent upon two things, the number of trials and the probability of success. The sample proportion is the number of successes divided by the number of trials. So we just divide this formula by n, we get this, and then we're going to manipulate this a little bit by putting this n inside the radical by squaring it. So if I want to put it inside, I have to square it because this is square root, right? So the square root of n squared is n. And then simplifying by canceling out the n's. So this n cancels with the squared here. Okay, and this is our formula right here for the standard deviation of a sampling distribution of a proportion. Okay, so let's take a look at what impacts we can see from different sample sizes and different probabilities of success. So right now we're going to look at this Rossmann-Chance applet. It says run a sample, n equals 50. That's my sample size is 50. And the proportion of orange candies is equal to 0.45. So here is the Rossmann-Chance applet. Okay, so it says 0.45. And my sample size is 50. And it says just, I'm going to make this a little faster. I'm going to do 400 samples all at once. So here we go. Take a look at what we have. You can see this is sort of normal, right? The middle of the distribution is right around 0.45, which is my probability of getting an orange, right? That's my proportion. My population proportion is about 0.45. And you can see the spread goes from about 0.28 up to about 0.68, right? And if we use the formula, let's just see what the standard deviation would be. It's the second square root of P1 minus P, so 0.45 times 0.55 divided by n, in this case n is 50, and that comes out to be about 0.07. So one standard deviation away from 0.45 would be about 0.52, so that's about here, and going the other way is about 0.38. Right, so you can see one standard deviation, two standard deviations would be about this much, and then three standard deviations would more or less include everything. Let's see, I'm going to go back here. All right, so that was the first one. Now it says take 400 samples of size n equals 50. So let's see what happens when we do 50. Oh, I did 50. What did I do? What was I supposed to do before? Hold on a second. I think I made a mistake. 50. All right, we did that already. All right, so now let's change the proportion to 0.15. N is 20, and then we're going to try n is 50. So first we're going to change this to 0.15, and I'm going to make this 20. And I want you to look at the distribution when I draw 400 samples. What do you see? Does this look normal? Not really. Notice this is a little bit skewed to the right, so it's not really normal. There's a reason for that. I'll get to it in just a minute. And then if I change the number of candies to 50 with 0.15, let's see what that's going to look like. And it's looking a little more normal, but still just slightly skewed. And now I'm going to change my number of candies to 100. And this is a little bit more normal. Let's do another 400 just to see. Okay, so you can see it's getting to be more normal. So it turns out there's a rule for this. Okay, so for what combinations of n and p is the distribution approximately normal? And summarize our findings. So before I go to what I was just talking about, let's look at this. As the sample size increases, the spread decreases, and the distribution becomes more normal. So that's what we've noticed. Okay, the sampling distribution, in some cases, depending on n and p, the sampling distribution of p hat, the sampling distribution of the sample proportion, can be approximated by a normal curve, which means we can use normal probabilities to solve problems. The center is the population proportion p, and the spread, as the sample size increases, the sample standard deviation decreases. I should type this to be easier. Decreases. So the spread gets smaller as the sample size gets bigger. All right, I'm going to skip this slide. It's just repetitious. Okay, so large counts condition says when these conditions are met, so when NP is greater than or equal to 10 and N1 minus P is also greater than or equal to 10, the sampling distribution is approximately normal. So in our examples, when P was equal to 0.15 and N was 20, then NP was 3, and we got something that wasn't normal. When P was 0.15 and N was 50, then 0.15 times 50 is 7, still less than 10, still not normal. It was getting closer, but it was still not normal. But when we went to P equals 0.15, N equals 100, then 0.15 times 100 is 15. This is closer to normal. All right, so this is the rule. This is called the large counts condition. When both of these conditions are met, the sampling distribution of p hat is approximately normal. Now you have to check both of them because, for example, if this was 0.85 instead of 0.15, then NP would be more than 10, but N1 minus P would be 3, and it still would not be normal. Okay, so you have to have both NP and N1 minus P. And this just says the same thing again, okay? The sampling distribution, the mean is the population proportion P. The standard deviation is given by this formula as long as the 10% condition is satisfied. I didn't mention that, but we still can't sample more than 10% of our population. As N increases, the sampling distribution becomes approximately normal, and here's the condition to check for that. And just to review some of our notation, p hat is our sample proportion, so it's the number of successes divided by the size. Mu of p hat represents the mean of the sampling distribution of p hat, of the sample proportion. Okay? And sigma p hat is the standard deviation. Okay, so this actually is going to be equal to P. Let me go back here. P. And the standard deviation, let's see if I can move this one. Sigma of p hat is equal to the square root of P1 minus P divided by N. Okay? And this is standard deviation of the sampling distribution of p hat. So what does that mean? This is just one slide that kind of summarizes what we've said. Over here we have a population with proportion P of successes. We take different samples. Sample 1, sample 2, sample 3, and so on. Each one gives us a proportion, okay, a sample proportion. We plot all those sample proportions. We will end up with a normal distribution where the mean is P, which is the population proportion, and the standard deviation given by this formula. I think that's all there is. Yes, that is it. So, I know this might be confusing. I would suggest that you go through this and go look through the book and read the examples in the book, and hopefully you'll be able to make some sense out of this, and we will talk about it at our next class.